for this program is provided by Annenberg CPD to advance excellent teaching.
Set out to prepare these lectures on magnetism for you. I did what anybody else would do under the circumstances. I went to the library to get a few books and find out what the subject was about. Well, it turns out that our library isn't completely up to date on the subject of magnetism, and so the only book on the subject that I could find there, at least the most recent book that I could find there, is this one, which came out in the year 1600. It's called De Magnete, and it's written by a man named William Gilbert. William Gilbert was born in 1544 and lived to 1603. That makes him a contemporary, for example, of Kepler and Galileo. He was a physician. He actually got his MD degree in 1569 at the University of Cambridge. And he became a prominent London physician, and eventually in the year 1600, he was named personal physician to Queen Elizabeth I. Unfortunately, he apparently wasn't very good at it because she died almost immediately. However, when he was not busy applying leeches to unfortunate sovereigns, he spent his time studying magnetism. The fact is that the only personal bequest that Queen Elizabeth made when she died was a sum of money for William Gilbert so that he could go on studying magnetism. Gilbert, as a matter of fact, discovered that you could destroy the magnetism of a magnetic material by heating it up. Gilbert made a number of other important discoveries about magnetism. For example, he found out how you could take a magnet, a permanent magnet, and make it even stronger by stroking it with another magnet. He found out that if you took an iron bar and kept it strictly aligned for a long time, it would gradually become magnetized. And perhaps his most important discovery of all was that the Earth itself behaves just like a giant magnet. Well, a few more facts about magnetism have been discovered since the time of Gilbert, and that's what I would like to tell you about today.
Of all the magnets on Earth, none is quite so grand as the Earth itself. In his Elizabethan study, Dr. William Gilbert had discovered that fact. Since then, scientists have discovered that most of the planets have magnetic fields. So do the stars, and especially the sun. In fact, much of the universe is like an extended family of magnets. As in any family, each member can have a significant effect on the others. Whether at the North Pole or here at the South, nowhere else is the Earth's magnetism felt or studied with as much intensity. This can be a brutal environment, but it's not without certain rewards, such as meeting the native inhabitants. Or experiencing the aurora, which just may be the greatest show on Earth. It's produced by charged particles from the sun and directed by the Earth's magnetic field. But exactly what is magnetism?
Just about everybody has played with magnets at one time or another, so you probably already know quite a bit about magnetism. For example, you probably know that you can use a magnet to pick up a paper box, provided, of course, that it's full of steel paper clips. I imagine you also know that you cannot use a magnet to pick up a piece of aluminum like that, or to pick up a piece of copper like that. In other words, some materials are magnetic and others are not. One thing you may not know is that something that is magnetic can have its magnetism destroyed just by heating it. For example, this is an iron wire. And you can see that it's magnetic because it's being held up right now by being attached to this ball magnet. I'm going to destroy the magnetism of that iron wire by heating it. And I'll do that by passing an immense current through it. Let me just do that. Now, as it warms up, you'll see that the wire starts to sag, but I'll have to get it almost red hot before it will fall off the magnet. I'll have to put a little more current in still. Now watch, and there it goes. When it got hot enough, it destroyed its magnetism and fell off the wire. Now, of course, that I've disconnected the current, it's cooling down, and when it gets cool enough, I should be able to make it stick back to the magnet again, like that. So, magnetism can be destroyed by heating, and it's restored when the material cools down again. And that's not true only of iron. It's true of other materials as well. I have here something that looks like just another hunk of ordinary iron, but it isn't. This is a very rare metal, which is known as gadolinium. Gadolinium is non-magnetic at room temperature. That is to say, it will not stick to this bar magnet. But that's only because room temperature is already so hot for gadolinium that its magnetism has been destroyed. If I cool it just a little bit below room temperature, it will become magnetic again. And I can do that, I can cool it down just by dipping it in this liquid nitrogen. Watch. I just have to hold it in here long enough for it to get cold enough to become magnetic. Okay, let's try it now. And there you can see now it's magnetic. Now it's actually magnetic only on one side because I only made one side cold. If I try the other side like this, it won't stick to the magnet. Only the side that's cold will actually stick like that. So, you see, magnetism can be destroyed by heating. It can be restored by cooling again in magnetic materials.
Hot or cold, in the form of a simple magnet or the spectacular aurora. What is the essential nature of magnetism? The equation for the force between magnetic poles resembles the equation for the force between electric charges, or the force between gravitational masses. Like electric charges, magnetic poles come in two kinds, called north and south. Opposite poles attract, and like poles repel. Unlike electric charges, magnetic poles always come in equal and opposite pairs. If you try to cut a magnet in two, to separate the two poles, the cut-end points create their own poles. So each fragment still has a north and a south pole. And it's just that difference between electric charges and magnetic poles that lead us to the question, can a single magnetic pole exist all by itself anywhere in the cosmos? According to certain theories, it can. Theoretically, some single magnetic poles, called magnetic monopoles, do exist. And they have existed ever since and as a result of the Big Bang. But if magnetic monopoles came into being then, where in the world are they now? A number of scientists have been searching for magnetic monopoles, but none have been found as yet. In the meantime, there are still plenty of magnetic dipoles to go around. Magnetic dipoles are two poles forever bound together into a single magnet. And they go all the way back to William Gilbert.
William Gilbert, the man who founded the study of magnetism, characterized the Earth as a giant magnet. The Earth does have an intrinsic magnetic field, and it very much is that of a giant magnet. The Earth's magnetic lines of force leave the surface in one hemisphere and return in another hemisphere, and the pattern of those lines of force is very similar to that of a bar magnet.
The magnetic field of a magnet, with its two poles, is similar in form to the electric field of two equal and opposite charges. A circular loop of electric current also creates a magnetic field of this form. And so does every proton, every neutron, and every electron in the universe. And the Earth itself has a dipole field that happens to point south, which is why compass needles on Earth point north. That point can be very useful at times, especially at a time like this. These Marines are using a compass to find their way back to camp. Soldiers as well as sailors have long used the compass to get themselves from here to there, over a hillside, or around the world. And to the extent they've succeeded, it's been because the magnetic needle of a compass always points north. But how does a compass work? Or in other words, what actually happens to a magnet in a magnetic field? In any magnetic field, a magnet experiences equal and opposite forces at its poles, so that it tends to line up with the field. In other words, the field exerts a torque that tends to make the North Pole point in the direction of the field. In fact, that's how the direction of the field is defined. No matter the destination, the magnetic needle of a compass can point the way, because it lines up with the field of the Earth.
But if according to the map, that's...
At least it does so here on the surface. But what happens farther afield, above the surface of the Earth? In fact, how far does the Earth's magnetic field extend?
About 52 degrees.
Originally, people thought that the Earth's dipole field extended indefinitely into space, but now we know that that's not the case, that it's actually confined in the solar direction by the wind, the solar wind from the sun that impinges on it continuously, and it confines it to a distance of on the order of 40,000 kilometers in the solar direction, and in the opposite direction, in the tail direction, it extends for millions of kilometers as far as we know.
The Earth's tail, which is not unlike a comet's, is actually made up of magnetic flux. Magnetic flux is defined in perfect analogy to electric flux as the flow of the field through any surface. The electric flux through a small element of surface is equal to the area times the component of electric field perpendicular to it. The total flux is the sum, or integral, of all the flux through the surface. The flux through any closed surface is equal to a constant times the charge inside, sometimes written as Q over epsilon sub 0. This is called Gauss's law. For an electric dipole, Gauss's law applies by balancing outward flux from the positive charge against inward flux toward the negative charge. So the total flux, like the charge, is 0. Magnetic flux is defined in exactly the same way. In concept, flux is a measure of the total number of lines of force passing through any surface. But since all magnets are dipoles, the total magnetic flux through any closed surface is always 0. The outward flux from the north poles is always cancelled by inward flux toward the south poles. This is Gauss's law for magnetism. As for any other magnet then, the total magnetic flux out of the Earth exactly equals the flux into the Earth. But just where does the planet's flux come from?
The Earth's main magnetic field we know to be caused by the flow of large-scale electric currents deep inside the Earth. There are other components to the field, but the main field, the dipolar component, is associated with these currents. We don't know exactly how the magnetic field is produced. We don't have an accepted model in detail for the production mechanism. However, we know it's somehow related to the motion of these molten conducting materials and the rotation of the Earth, and those materials are, especially in the deep interior, primarily molten nickel and iron.
Because the Earth's magnetic field stems from the rotation of the Earth, it more or less lines up with that rotation. In reality, the whole field wobbles around once each day because it's off by about 11.5 degrees. That difference has been known since antiquity, and explorers have always had to compensate for it, some more successfully than others. But even for the best sailors, the Earth's magnetic field doesn't quite stay put.
The Earth's magnetic field is continuously changing. As a matter of fact, the navigational charts, the things that we use to determine our direction by using measurements with compasses, have to be changed every so often in order to be sufficiently accurate for navigational purposes. So the field is constantly changing. Over the scales of millions of years, it changes much more dramatically than that, and in fact the polarity actually reverses, not in a periodic way, but in an aperiodic way, nevertheless frequently in terms of geologic time.
From a geologic point of view, this flipping of the Earth's magnetic poles north for south takes place fairly often, about every 500,000 years or so. Compare that cycle to how often the Sun changes polarity.
The field of the Sun changes direction every 11 years. This is a remarkable process which starts with the sunspots. The magnetic polarity of sunspots is different in each successive 11-year cycle. A sunspot is a dark region that we see on the surface of the Sun, which we find is the result of intense magnetic fields. The sunspots always occur in pairs because there are no magnetic monopoles, so I always have to have a north and a south, or a plus or a minus polarity together. So I tend to see two big sunspots, and the magnetic lines of force will go from one sunspot into another. We see the sunspots come up as though a big tube of magnetic flux has come up from below the surface, and we see the intersection of this tube with the surface as a very strong sunspot.
Very strong sunspots create very strong consequences. Among the most spectacular are the solar flares. There's also the solar wind, not as obvious but equally evident when it whips out to play havoc with the Earth's magnetic field.
The sun is the origin of the solar wind, which is a high-speed outflow of all the material in the atmosphere of the sun, and this happens in a curious way. The outer atmosphere of the sun, which we call the solar corona, is very hot. That's what we see around the sun in a total solar eclipse, if you ever get to see one. It's 1,000,000 degrees in temperature. Now, when the gas gets that hot, it becomes easier for it to escape from the sun. Because it's so hot, the conductivity is high, and so the temperature of the solar wind stays high a long way out. Even at the Earth, it's quite high. As a result of that, the gas can escape from the sun, and it flows outward under control of the magnetic field. In fact, they live together. The solar wind drags out the lines of force, and then the lines of force control the material. So the sun is responsible for the solar wind by heating the material in the corona, ultimately. If I have a gas of charged particles threaded by a magnetic field, the charged particles can move quite easily along the lines of force. But when they try to move at a direction across the lines of force, they spiral around it, and that spiraling is produced by what we call the Lorentz force.
A magnetic field applies no force at all to an electric charge at rest. However, if the electric charge is in motion, there's a magnetic force called the Lorentz force. It's perpendicular to both the field and to the direction of motion of the charge. The force is conveniently expressed using the vector cross product. Because the magnetic force on a moving electric charge is always perpendicular to the velocity, the force doesn't speed it up or slow it down. Instead, charges tend to curve around the field in circular or helical paths. In non-uniform magnetic fields, electric charges can be trapped, as they are, for example, in the Van Allen radiation belts. Near the polar regions, charged particles sometimes get close enough to strike the atmosphere, giving off light like electrons striking a television screen. That's the origin of the spectacular aurora at the North and South Poles. In general, however, the effect of the magnetic field is to keep charged particles away from the Earth.
The Earth's magnetic field acts as a shield to us, and it really protects us from energetic particles from the sun and from cosmic rays. So in fact, we're fortunate to have the Earth's magnetic field. It really is one of the things that promotes life on Earth as we know it. Some other planets do have magnetic fields. Jupiter and Saturn and Uranus have magnetic fields. Venus, for example, does not have a magnetic field. And in fact, even though before people used to call Venus Earth's twin, or that they were the twin planets because they were similar in size and almost the same distance from the sun, now we know, in fact, that that's not the case, that really Venus is like an Earth that's gone bad. And part of the reason that it's gone bad is that it doesn't have a magnetic field to protect it the way we do on Earth.
When William Gilbert claimed that the Earth behaved like a giant magnet, little did he realize that he had hit upon one of the critical ingredients that make life on Earth possible.
So, we really have learned a lot about the nature of magnetism. But we shouldn't forget that it all started with this book by William Gilbert. This book is actually extremely rare. There are thought to be something like 60-odd first editions of William Gilbert in the entire world. And this particular copy of it is very special because it has an inscription on the front page which is thought to have been written by Gilbert himself. If it was, then this is the only known example of Gilbert's handwriting. However, rare and valuable as this book is, it isn't the oldest thing we have written about magnetism. In fact, there's a manuscript about magnetism that came more than 300 years before Gilbert's book. It was written by a man named Pierre de Méricourt, also known as Peter Peregrinus. That means pilgrim, so you can think of him as Pete the Pilgrim. Let me tell you everything that's known about this shadowy figure. We have a manuscript of his. It's called an epistola, which is the Latin word for letter, so it's a letter that he wrote. The title of the letter is Letter on the Magnet of Peter Peregrinus of Méricourt to Sigirus of Foucacourt, soldier, period, end of title. Then the letter goes on. The letter, the manuscript, is a description of the behavior of magnets, various things about magnetism, and tell us nothing at all about Peter himself. And at the end of the letter, at the very end, the conclusion says, completed in camp at the siege of Lucera on the year of our Lord, 1269, 8th day of August. And that is everything that is known about Peter Peregrinus. Based on that information, historians have told us that he was an engineer in the army of Charles of Anjou, king of Sicily, that he was of noble birth, that he came from the town of Maharicourt in Picardy, that he was a theologian, and even that he was a Franciscan. How do historians know all of that? I think it's what's called the scholarly imagination. Well, scholars are not the only ones who have imaginations. Pierre himself, Peter Peregrinus, had an imagination. He was the very first person to invent a magnetic perpetual motion machine. It was the first of many. And when it didn't work, as all of the others that followed it didn't work, he was the first one to blame it on the guy who made it for him. But his shrewd observations about the behavior of magnets made his manuscript extremely valuable. There are 31 known copies of that manuscript, and by the standards of the Middle Ages, before the invention of the printing press, that means that his manuscript was a smash bestseller. At least one of those copies fell into the hands of William Gilbert because Gilbert drew on heavily and cited heavily this work, this letter, that came to us from the mists of time. And speaking of time, we're out of it, and so I'll see you next time.
Funding for this program is provided by Annenberg CPD to advance excellent teaching. For information about this and other Annenberg CPP programs, call 1-800-LEARNER and visit us at www